Yes, yes, sir. Good morning, everyone. Still, we are waiting for remaining 20 students. Maybe one. Good morning, Talib. I think tomorrow or day after tomorrow, you will get your first internal marks. Tell others to join quickly. I have already shared the message. Okay, guys. Now we are starting the last topic of module 4, which is method of generating functions. Okay, this method is a method of solving those recurrence relations which are non-homogeneous. Okay, now you know the way, you know the equation, kind of equations. Yesterday I discussed about it. So yesterday we did we tackled few means non-homogeneous recurrence relations with some specific condition when C1 is -1, or after that uh, we know the solution an is ANH plus ANP. So the main task is ANH is easily recognizable, but ANP will depend on FN. So for a specific FN, we have specific ANPs. So I showed those things yesterday. Now another method is there called the method of generating function to tackle these those problems. So one of the example I'm showing. So I'm taking one example, an minus 3an minus 1 is equal to 1 is equal to n, or a0 is equal to 1. So this equation is nothing but a non-homogeneous recurrence relation because of this n. Okay, and it is of first order because an is depending only on an minus 1. So how can we tackle this situation? See, we have so many equations here. If we start from n is equal to 1, so we have a1 minus 3 a0 is equal to 1. For n is equal to 2, this equation will be a2 minus 3a1 is equal to 2. Similarly, for n, I can write an minus 3 an minus 1, right? So we have many multiple equations here. So now if I multi in this method, what we will do, we will try to use the concept of generating function. Okay, so you know the generating function, it will be represented in terms of polynomial. So we are trying to create polynomials. Okay, so for that, to create a polynomial, variable is required. So here we don't have any variable, right? So we will multiply this first equation by x. Uh, this is gonna be the first equation, sorry. The first equation by x, the second equation by x square, and nth equation by x to the power n. So after multiplying 1 by x, 2 by x square, and nth by x to the power n, and adding, first we multiply and then we will add. So if I multiply first by x, we get a1x minus 3 a0x is equal to x. Second by x square, and nth by x to the power n. Okay, so we have another set of equation now. Now if we add all these new equations, we will definitely get a1x plus a2x square up to anxn negative 3 a0 x plus a1 x square plus an minus 1 x to the power n, the addition of these all, the addition of right hand sides, right? So For the whole addition, I am using summation. For these equations addition, I am using summation. So summation, I'm starting from 1 to n here. So n is equal to 1 to, it will go up later n as well. So I'm taking infinity. So I can represent it as an x to the power n. This summation is representing the summation of the first term for all equation. Then -3 summation again. Now n is starting from 0. But if I start from 1 here as well, I will have to take 1x here. Okay, from 1 to infinity, 0 to infinity. Uh, Here we have the first equation, we have a0. So we will write in the nth equation, we will write an minus 1. Okay, and x to the power 1, we will starting from x to the power 1. So we will write x to the power n. Here I am writing 1. If here I am writing 1, I will write, here I'm writing 0. So this is gonna be -1. N is equal to 0, it is gonna be -1. So I should write n here, not n minus 1. Yeah, x to the power. I'm starting with 1, so I will write n minus 1 here, forgetting 0. And x to the power 1, yes. Now I'm writing correctly. So n minus 1 is there, is equal to, if I add these terms, so 1x, 2x square, nxn. So it's gonna be the summation of nxn. And starting with the n is equal to 1, so I will write n is equal to 1 to infinity. So this is gonna be the overall summation. Okay. Now after this, since we have a minus n minus 1, a n minus 1 here, so I will try to write this term as n minus 1. So I will take x outside from summation. So I will write x here. Okay, after this, since we are likely to use generating function to solve this kind of equation, now that's why this method is called method of generating function, because generating function is helpful to find out the solution. So ordinarily we are considering fx is equal to sum of n is equal to 0 to infinity an x to the power n as a solution of this generating function, because it will generate the sequence a0, a1, a2, and so on. So it will depend on your the term which function you will consider. So here we have this kind of polynomial, so that's why I'm considering this kind of polynomial as fx, fnx, for representing the nth term. Okay, so this is going to be the solution on fx, right? So see, if I compare this with this, here one term is missing. Here we have extra term a0, because n is starting with 0. Here we don't have a0. So this sum, if I am writing in terms of f, what I will write fx minus a0, because a0 is missing. Now in the second, if I compare this, it's starting with 1. So it's nothing but a0 x to the power 0, means a0 is already present here. So this is nothing but your f. Okay, every term of f is present here. So that's why it is fx. Right? And this series, if I consider, this series is nothing but uh, x plus 2x square plus 3x cube and so on. Right? So we have to generate 1, 2, 3, and so on. So which series, which function will work, which generating function will work to generate 1, 2, 3, and so on. Okay, there is a generating function called x upon uh, 1 minus x square. This function will generate this series of this series. So that is a sequence. So we will write this in place of this x upon 1 minus x square. So now we can solve this equation for f. Okay, and we have to find out the solution. That is, we have to find out the coefficient of x to the power n. So if uh, uh, you completed this, I can erase the screen. Otherwise, I can wait. Okay, after this, yeah, solve for f here. So 1 minus 3x f minus AC was given 1. So minus 1 is equal to x upon 1 minus x square. So fx is gonna be x upon 1 minus 3x 1 minus x square. So do this you have to solve using partial fraction. So now I am dealing this to get the partial fraction. So I will write it as a upon 1 minus 3x plus b upon 1 minus x plus c upon 1 minus x square. right? So this is gonna be a into 1 minus x square plus b into 1 minus x 1 minus 3x plus c into 1 minus 3x, right, which is equal to x. The numerator I'm comparing. Now, if I take some specific values of x, suppose I'm taking x is equal to 1. So for x is equal to 1, I get one equation. This is going to be 0. Second term is going to be 0. So x is equal to 1, I get minus 2c. Minus 2c is equal to 1. So c is minus 1 by 2. Similarly, I can find a and b for specific values of x. So now I'm taking x is equal to 1 by 3. So for x 1 by 3, this number is going to be 1 minus 1 by 3 means 2 by 3 square. So 4 by 3a plus, this is going to be 0, this is going to be 0. So 4 by 3a is 1 by 3. So a is going to be 1 by 4. Now after this, we can take x is equal to 0. So if I'm taking x is equal to 0, I get a plus b plus c is equal to 0. So we know a and c now, so we can easily get b. Minus 1 by 4. C was minus 1 by 2, so this is going to be plus, so 1 by 4, right? So now we have ABC. So the partial fraction of this will be recognizable. So fx is equal to a upon, means 1 by 4 upon 1 minus 3x plus b upon b means b is also 1 by 4, 1 minus x. C is minus 1 by 2. Right? Plus 1 upon 1 minus 3x. This was the. Okay, so this is your fx. Now your target is to find out the coefficient of x to the power n. Get the solution. So you know the expansion of this 1 upon 1 minus 3x. You know the expansion of 1 upon 1 minus x, 1 upon 1 minus x square. These are like terms, so we can add 1 plus 4 plus 1. So it's gonna be 5 by 4. 1 minus 3x inverse. So you can apply the binomial expansion or the generating function concept to get these uh, values. Okay, so how can we expand this? Tell me what's gonna be the expansion. If I collect coefficient of x to the power n, so from here, uh, the expansion will be 1 plus 3x square plus 3x, 1 plus 3x plus 3x square plus 3x cube plus 3x power 4 and so on. So the nth term will be 3x to the power n. So 5 by 4, 3 to the power n. This is going to be the coefficient of x to the power n for this term. Now for the second term, the expansion will be 1 plus x plus x square plus x cube. So x power n will be that term. So 1 by 4 only I'll get. And here if I put 1 minus x to the power minus 2, negative power is there with negative sign. So here I will use that concept minus 2 choose 0. This is going to be the expansion minus 2 choose 0 plus minus 2 choose 1 minus x plus minus 2 choose 2 minus x square and so on. So if I consider nth term, so it's going to be minus 2 choose n x to the minus 1 to the power n. This is going to be the coefficient of x power n for the third one. It's 1 by 2. Okay, so now we can solve this whole. Minus 2, this we can write as in a similar fashion, no problem. But you can solve the last two. This you can solve. So minus n choose r, you know. Minus n choose r is equal to n plus r minus 1 choose r. This formula you will apply whenever you have this negative sign and choose, so you will apply this formula. So n plus r minus 1 choose r means 2 plus n minus 1 choose n, right? So this you can solve, right? So n plus 1 choose n. N plus 1 choose n is nothing but factorial n plus 1 upon factorial n factorial n plus 1 minus n is factorial 1. So n plus 1. So n plus 1 negative 1 bar. So this is going to be your answer. So this is another method to tackle this non-homogeneous differential solution, the method of generating function. Any doubt in this solution? We have to convert this equation in terms of summation, and then we will use the concept of generating function. That is, we will assume fx in terms of generating function, and then we'll find out the coefficient of x to the power to get the answer. Any doubt? I want to listen your voice. Any doubt in the solution? This method. Kirtana, Austin, okay. Okay, now if I am taking A and R as choose R objects from N objects with repetition. Okay, and if I have to generate, if I have to create a recurrence relation for this condition, what's going to be the recurrence relation of selecting, of choosing R objects from the N objects with repetition? So what's going to be that recurrence relation? So suppose after choosing R objects, okay, initially we have these objects B1, B2, Bn. From these N objects, we are choosing R objects with repetition. So there will be two choices. Either one, suppose I'm selecting B1. Either B1 is selected, either B1 is not selected, or B1 is selected at least once. At least once means more than once is also possible. So these two conditions are there. So if B1 is not selected, that is, I am removing B1 from here. Okay, that is, I am selecting R objects from N minus 1 objects now. Okay, so A and R is representing the number of ways of choosing R objects from B N objects. So in that case, since B1 is I'm not selecting, so we have only N minus 1 objects now. So I will choose R objects from N minus 1 objects. So there will be A N minus 1 R number of ways to do this when B1 is not selected. Now, second condition, if B1 is selected at least once, okay, B1 has been selected means B1 is present on those R objects now, right? That is, if I remove B1, there will be R minus 1 objects because B1 is selecting at least once, right? So I will have to remove this B1 at least once from these R objects. So now we have R minus 1 objects to choose from those N objects. So there will be A N R minus 1 ways to select B1 at least once. For the remaining, I'm saying, after selecting B1, these number of ways will be remaining. So A and R is nothing but the summation of these two mutually exclusive conditions. Both are mutually exclusive conditions because both are at the intersection of zero, right? Because There's no intersection, no common things. For in first we are saying B1 is not selected, and second we are saying B1 is at least one selected. So both are mutually exclusive. So A and R is gonna be, since both are mutually exclusive, so this is gonna be the sum of these two results. Okay, so this is gonna be the recurrence relation. Now, how can you solve this? Using method of generating function. So you will have to generate x first for creating polynomials. So I'm taking, since I'm choosing r objects here, so I'm taking x to the power r. So multiply x to the power r in both sides. And after this, I'm taking summation from 1 to infinity. R varies from 1 to infinity. Right? And I'm taking fx as since we have this kind of function now, so I'm taking fx as n is equal to 0 to infinity a n r. R varies from 0 to infinity. No, r is fixed. So I will consider a n0 here as well. A n0. That is, I'm choosing 0 objects from n objects. So how many ways will be there? I'm not choosing anything, but there will be one way. That is, I'm not choosing anything. First way, first and last way. So a and 0 is going to be 1. So, and if anyhow we have a 0 r, that is, I don't have any element, I am choosing r elements from any no element. There will not be any way, right? So a0r is going to be 0. So these two conditions are boundary conditions. Whenever required, you can use these conditions. Okay, so after taking summation, I will put this value f. I will try to convert this equation in terms of f. So r is 1. So a0 is a n0 is missing here. Okay, and f we are starting from a n0. So a n0 is missing. So this is fx minus if this is representing fn minus a n0. Here a0 is present. Okay, a0 r is present. R is varying right now. Okay. Sorry, a n minus 1 1. We are starting from a n minus 1 1 here. So okay, here we have r and r minus 1. So I will convert this power as r minus 1. I will take x outside here. Okay. So this number is representing f. This is your f. So fn plus x I'm taking from outside, and no, since we are starting from n minus 1, this is representing n minus 1, fn minus 1 plus x. I'm taking x outside, so x to the power r minus 1 will come here. So this is representing f, because n is here present, r minus 1 x r minus 1. This is representing fn. And a n zero we can put from here, right? So fn uh, minus xfn, this I'm transferring there, and this is your one, right? Negative one. So one plus fn minus one. So one minus xfn. So fn is equal to r is equal to one. Yeah, a zero r will also come here, right? So a zero r is not represent, means here no, here he will, we will not get a zero r, but in fn we have a zero r, so that's why I will sorry, a n zero, not yeah, we are starting from r is equal to 0 in fn, right? So here we are starting from 1, so this a n 0 is missing here as well, so that's why 1 will come, fn minus 1 minus 1 will come here. So this 1 will cancel out, this 1 will not come here, so we'll get fn is equal to fn minus 1 upon 1 minus x, right? So similarly, if I starting from n is equal to 5, I can write f5 as f4 upon 1 minus 6. And if I write f4, it's gonna be f3 upon 1 minus 6. So if I put f4 here, I'll get f3 upon 1 minus x square, right? So overall, I will get fn as fn minus 1 upon 1 minus x to the power n. And if I want to find out the coefficient of this 1 minus x to the power minus n, we have to find out the coefficient of x to the power n into this expansion 1 minus x to the power minus n. And you know the this series, right? Minus n choose 0, plus minus n choose 1, negative x, and so on. So at the nth term will be minus n choose, sorry, the coefficient of x to the power r's, minus n choose r, negative 1 to the power r. Okay, so this, you know, I have shown you the formula. So n plus r minus 1 choose r with negative 1 to the power n, r not n. Okay, so this is gonna be your answer for this reconciliation. The coefficient of x to the power r in this expansion. So I hope you are getting this solution as well. We are trying to find out the reconciliation when we choose r objects from n objects with repetition. So this is going to be the way of generating reconciliation and finding the solution from the method of generating function. Here I am taking this generating function to find out the solution. I am missing x to the power r here. Any doubt in this solution? Because you have to attend the second lecture now. Quickly say, I'll take your attendance online, no problem. Okay, so I am finishing this module now. So from tomorrow, I will start the fifth module, the graph theory part. So if you have any doubt, you can say. I will give you the questions as well related to third and fourth module and the previous modules as well together. And I hope you will be, you will get ready on time for presentation from the next week. Thank you. And now you can leave. Thank you if you don't have any doubt.